Hello everyone, welcome to the course Geotechnical Engineering 2. So in this module number 3 and lecture number 8, we will be discussing on the earth retaining structures. Okay, so let us now look at the course outline once again. So if you look at the course outline, initially we have understood what do we mean by slope, okay, and as well as the factor of safety, and then some of the slope stability methods in determination of factor of safety, as well as we have understood the stability of slopes for embankments as well as dams. Okay, so now we will be discussing the earth retaining structures. Okay, so what exactly do we mean by earth retaining structure or a retaining wall? That means if you consider any soil mass, okay, if you consider any soil mass and if the soil mass is supported by any vertical support, and that is known as a retaining structure. Okay, so now let us look at the diagram now. So let us say this is a vertical wall, okay, and here there is some soil. This is the ground level, and let us say this entire region is soil. Okay, that means this is a retaining wall. This is a retaining wall. This is a retaining wall, let us say, and this is trying to resist this soil. This is the soil. Okay, so any structure that is trying to resist the soil is nothing but retaining wall. Okay, so what exactly do we consider here is that the line of action of the force, okay, the amount of force that is coming, that means the magnitude as well as the line of action on this retaining wall. Okay, so that there will be some movement of this retaining wall. Okay, so that is one entity. So we will consider some of the factors in case of design of retaining wall. Okay, so as I've stated, the magnitude and the line of action of the soil, okay, amount of pressure that is coming onto the retaining wall, and then the lateral earth pressure. That means what is the lateral earth pressure that is coming onto the retaining wall. So these two are some of the important parameters in case of retaining wall design, okay, or understanding the analysis of retaining wall. Okay, apart from that, it depends on various number of factors. Okay, that is the mode of movement of the wall, that means in which direction the wall is moving. Okay, and the other one is the flexibility of the wall. Okay, the flexibility of the wall, and then the properties of the soil. Okay, so whatever soil that retaining wall is resisting, that also is one of the factor. Apart from that, the drainage conditions, that means whether it is in partially saturated state or saturated state or submerged state or any dry state. Okay, so these are some of the important factors on which a retaining wall analysis or design is based. Okay, and now coming to where exactly do we consider this earth pressure, since we are talking about the lateral earth pressure, so where do we exactly consider this? So, in calculating the earth pressure, it is necessary in order to design structures. That means we need this lateral earth pressure, as I've stated, to design the structure, say retaining wall. Okay, so as I've stated, the first example is the retaining wall. The other type is the bridge abutments. Okay, the other type is bulkheads. The other type is temporary earth support systems. Okay, and then we have basement walls. So in all these cases, the importance of lateral earth pressure is so much that we need to consider the lateral earth pressure and design any of these structures. Okay, so that is why the concept of lateral earth pressure is very much important. Now coming to the uses of retaining walls, so as I've stated, if you look at this, this is an embankment construction, so retaining walls are used here. Okay, and this embankment is supported so that the soil at this region does not move laterally. And if you look at here, if there is a cut made to any hillside, okay, then also a retaining wall is required so that it doesn't have any slope failure. Okay, the other type is a bridge abutment. Imagine there is a bridge construction here, so obviously the surrounding soil here which has to be supported, so a retaining wall is given here so that this is supported. And similarly the other one is the water storage. Okay, so along the river side or any shore, okay, there may be a requirement of retaining wall so that the soil doesn't slide away. Okay, so these are some of the examples. So apart from that, we have flood walls, okay, in case of river retaining. And the other type of retaining wall is a sheet pile type. That means it is a single very slim sort of arrangement, sheet pile in the form of sheet, which is either anchored to the soil. Okay, this is an anchorage to the soil. So this is one of the other type of example, and these are some of the locations where we use these retaining walls. Okay, now let us now look at the retaining wall. So the earth pressure is computed. Okay, as I've stated, the lateral earth pressure has to be used to design the structures. So to evaluate this lateral earth pressure, Rankine and Coulomb's theory are used. Okay, however, Terzagh's wedge theory is also used, but it is not quite convenient. So Rankine as well as Coulomb's theory is used. Now, so upon movement of the retaining wall, that means using these theories upon the movement of the retaining wall, either if you consider a retaining wall, I am a retaining wall and the surrounding is a soil. Okay, so based on the movement of this retaining wall, okay, it has been categorized into three categories. That is a, at rest condition. That means I am at rest condition. The other one is active pressure. Imagine above me there is soil. Okay, so if I'm moving away from the soil, then the pressure that is occurring laterally is nothing but my active earth pressure. Okay, and the other one is passive pressure. That means if I'm moving towards the soil, then it is passive pressure. So these are three different categories for lateral earth pressure based on the movement of the retaining wall. Okay, so these are considered. So now let us try to understand more in detail about these. Okay, and let us try to evaluate the lateral earth pressure. So now consider the lateral earth pressure now at rest condition. Okay, that means it is not subjected to any lateral movement. That means if I am stationary at that particular point, I am not moving. Okay, that means the wall is not moving, retaining wall. So in such case there is no lateral movement, so that means it is at rest condition. Okay, so now the retaining wall is firmly fixed. As I have stated, the retaining wall is firmly fixed and there is no rotation. Okay, that means it is not allowed to rotate. The other one, that means at rest condition is nothing but elastic equilibrium. That means at rest condition means it is known as elastic equilibrium, as no part of the soil, okay, above me there is soil, okay, in front of me there is soil, so that soil has not attained any plastic equilibrium. Okay, so in such state we may state that it is elastic equilibrium. That means the soil above me when I am in rest condition, it has not failed, because it is also stationary, because this wall is not moving. Clear now? So if you look at this particular diagram, so this is a retaining wall and there is soil here. Okay, so if you consider a soil element, in general we denote the vertical stress as sigma v and the horizontal stress as sigma h, that is nothing but our lateral stress. So if you consider an element at a depth z, okay, so if you want to evaluate, okay, the vertical stress, we know that gamma into z is nothing but sigma v. Okay, so in other aspects there is a relation for this lateral stress as well as this vertical stress. Okay, so that relation we have learnt in our earlier sections in GTE-I, okay, where it is denoted by a constant k. Okay, that constant is nothing but sigma x by sigma z. Okay, that means the horizontal stress to or vertical stress. So in this particular aspect, since it is at rest condition, it is denoted by k naught. Okay, that means it is the coefficient of lateral earth pressure, so it is denoted by k naught, and this is equal to sigma h by sigma z. Okay, or in this case it is sigma v. Okay, so that is how it is actually varying. Clear? So if we look at the stress diagram, in general it is in triangular form. Okay, because if we consider the lateral earth pressure sigma h, that is k naught into sigma v. Okay, so that is why if at depth z is equals to 0, the value of lateral earth pressure is 0, and as it increases gradually up to a height of h, it is increasing gradually. So that is why it is in the form of a triangle. So we will look at this more in detail in the upcoming sessions. Okay, now, so what do we mean by active pressure and passive pressure? So as I have stated, the soil tends to stretch horizontally. That means if this is a soil here, if the wall movement is backwards, okay, away from the soil, so that means it is trying to stretch. Okay, that means it is horizontally stretching. So in such case, the pressure that is there on a soil element is nothing but my active pressure. Okay, so retaining wall moves away from the backfill. And if you look at the passive pressure, that means the soil tends to compress horizontally. That means if the wall is moving towards soil the soil is now compressing. So that is why when the soil tends to compress horizontally, that means the retaining wall is now moving towards the backfill. The soil above me is generally known as the backfill, okay, or along the side of the retaining wall is known as backfill. So when it moves towards the backfill, it is known as passive pressure. So if you look at this particular diagram here, so this is at rest condition. So imagine this is a retaining wall of height h, and since there is no movement, so the soil is at rest and the retaining wall is at rest. Okay, and if you look at the active pressure, so this retaining wall is now moving away from the soil. Okay, so that means there is a wedge failure occurring. Either it may be a wedge failure or any other failure, but the failure is occurring in this manner. So such type of pressure is known as active pressure, and the soil is in active state. And if you look at this coil, the retaining wall is now moving towards the soil. So that is why this is known as a passive case. Okay, so this is what we have looked till now. So in these two aspects of active pressure as well as passive pressure, okay, so these two are nothing but in the state of plastic equilibrium. Okay, these two are in the state of plastic equilibrium. So that means here the soil is changing its state from elastic equilibrium to plastic equilibrium, or the soil is failing. Okay, so these are the state of plastic equilibrium. Clear? Now, so if you look at the pressure diagram, if you consider the x-axis as the movement of the wall and the y-axis as the earth pressure or the lateral earth pressure. Okay, so when the wall is now stationary, if you consider this as the wall stationary, that means there is no movement of the wall. Okay, no movement, no movement of the wall, that means it is at rest condition, it is at rest condition. So in such case, okay, the value of sigma will be somewhere here. Okay, the lateral earth pressure. So when the wall is now moving away, okay, when the wall is now moving away, that means the soil is now getting free. Okay, that means it is trying to stretch. So what happens, the actual pressure is now decreasing. So as the wall movement increases, there is a decrease in the active pressure. Okay, there is a decrease in the active pressure, and so that is why this is mentioned as active pressure. Okay, now as the wall is now moving towards the soil, that means it is trying to compress, that means more additional stress is acting on the soil. So that is why there is an increase in the stress in this manner. Okay, so that is why it is given as passive pressure. So that is the difference here, okay, between active state, at rest state, and passive state. Okay, so based on this, we will try to evaluate the lateral pressure for rest condition, and then the active pressure condition, and then the passive pressure condition. Okay, now, so at rest condition. So as we have looked earlier, this is the particular retaining wall, and let us consider a two-dimensional plane in this manner, soil element in this manner, which is having sigma v in the vertical direction and sigma h in the horizontal direction. So this is our lateral earth pressure, and let us consider this element is at a depth of z and the height of the retaining wall is h. Okay, and this is the lateral earth pressure diagram what I have stated earlier. So let us try to obtain this now. Okay, now considering the lateral earth pressure case, that means when it is at rest condition, so that means there is no movement, no movement. Okay, so that means when there is no lateral movement means the strain along the lateral direction is 0. So that indicates that, let us say, epsilon x is 0. That means strain along that particular direction is 0. So in such case, we know from the concept of strength of materials for any two-dimensional body or three-dimensional body, the strain is 0 indicates that 1 by E into, if the stress is sigma x, it will be sigma x minus mu into sigma z plus sigma y is equal to 0. Okay, for a three-dimensional body. So since sigma y and sigma x are same for the particular body, okay, since we are considering a two-dimensional body, so denoting this in this manner, so 1 by E into sigma x minus mu sigma x minus mu sigma z, okay, that is equal to 0. Since as sigma y is equal to sigma x, okay, so that is why we have written this particular term. Okay, on further simplification, this can be written as 1 by E into sigma x into 1 minus mu, okay, minus mu sigma z is equal to 0. So upon simplification, this can be written as, since E will go into that side, this will be sigma x is equal to mu into sigma z by 1 minus mu. Okay, so simply I can write down this as sigma x by sigma z is equals to mu by 1 minus mu. Okay, so from the previous concept what I have stated, or in geotechnical engineering 1 what we have studied, this sigma x by sigma z is nothing but some coefficient. Okay, so therefore this k is equal to sigma x by sigma z, and therefore it will be mu by 1 minus mu. Okay, where k is one particular coefficient. So in our particular case, okay, so we will be considering this coefficient. Okay, at rest condition we will consider this particular entity as k naught, that means coefficient of lateral earth pressure at rest condition. Okay, this is considered as coefficient of lateral earth pressure at rest condition, okay, so that is what we will consider this k naught. Okay, so for this particular case, let us now try to obtain the lateral earth pressure. So let us consider this as a ground level, and let us say there is an embankment there is an embankment in this manner. Okay, let the height of the embankment be capital H. Okay, and let the soil is having a unit weight of gamma. Okay, just for time being, and let us consider a small element for our analysis case, and let this be sigma v, and let this be sigma h. Okay, and let us consider this at a depth of z. Okay, so since this is the soil element, so for this particular soil element we know that the coefficient of lateral earth pressure constant K naught is given by sigma h by sigma v. Okay, we know this K naught is equals to sigma h by sigma v. So from our previous concepts we know that the vertical stress sigma v at a depth z is nothing but gamma into z. It is nothing but gamma into z. We know this particular thing. The vertical stress of a particular element at a depth z is nothing but gamma into z, whereas gamma is the unit weight of the soil, z is the depth at which we are finding out the vertical stress. This we have learnt in our stress distribution concepts. Okay, so from this particular equations, let us denote this as equation 1 and this as equation 2. So from these two equations I can simply write down as sigma h is equal to sigma v into k naught. So that is k naught into sigma v is gamma into depth z. Okay, so this is my lateral earth pressure at rest condition. This is my lateral earth pressure at rest condition. So depending upon various drainage conditions this formula may vary, because here the soil is just in partially saturated state, so I have denoted gamma. Let us say it is having some water table, so this value will vary. Okay, but however we need to determine the lateral earth pressure in this manner. So when it is at rest condition it is denoted by k naught. Okay, so for this particular case let us now consider this equation. Okay, let us consider this equation and use in this equation, if I have to draw a lateral stress diagram, okay, or lateral pressure diagram, when the depth is 0 sigma h is 0. That means when the depth is 0 at the ground level, so sigma h is 0. So therefore at this point sigma h is equal to 0. So at a particular depth z, okay, or let us consider at the bottom of the embankment at a height h, so it will be k naught gamma h. That means it has increased to k naught gamma h. That means if you look at this particular case, it is changing along the depth z. That means it is directly proportional to depth z. Okay, so that is why it is a linear variation and the diagram will be somewhat in this manner. So at this particular case here, this will be k naught gamma into h. So this is the lateral earth pressure at this location, and at this location it is 0. So somewhere in between at a depth z, say, okay, this will be k naught gamma z. Okay, so in this manner. So if you look at this particular case, so this is the lateral pressure here. That means this is a lateral pressure, k naught gamma z or k naught gamma h is the pressure at different depths. So if I have to represent this entire thing in the form of a lateral force, okay, so how do we consider the lateral force now? So it is considered in this manner. So if I say there are n number of lateral forces along this particular direction, okay, this is the lateral pressure diagram. So if I have to represent a lateral stress here, okay, it is denoted by the area, okay, the area of this particular stress diagram or pressure diagram. There it is nothing but, area is nothing but, since it is a triangle, it is half into base k naught gamma h into height. This height is h. As we know, it is till the embankment height, so it is h. So let me denote this is lateral force LF. So that is nothing but half k naught gamma h square. So this is the lateral force, and this lateral force will be acting through the centroid of this particular stress diagram. So for a triangle, the centroid will be somewhere, let us say it is at a depth of h by 3 or at a height of h by 3 from the base. So this will be half k naught gamma h square. Clear? So this is the lateral pressure. Okay. So this is at rest condition. The lateral pressure is k naught gamma h, and the lateral force is obtained as half into k naught gamma h square, which is at a distance of h by 3 from the base. Clear? So that is regarding the today's lecture. So in the upcoming lecture, we will be trying to discuss the lateral earth pressure for different cases, that is active case and passive case, based on Rankine's earth pressure theory. Okay, so that we will be discussing in the upcoming lecture. So that's it for today. Thank you very much. I hope you have understood this very well. Okay, have a very nice day.